What's the function of the first-order circuit? You may be wondering about this question now. From this lecture, we will use 3 lectures to introduce the applications of first-order circuits in energy processing and signal processing. You will be amazed that dynamic circuits have a wide applications with energy storage elements and 3-element methods. In the first lecture of the applications of first-order circuits, we'll discuss MOSFET. Firstly, let's have a review. For MOSFET, if the voltage between G and S is greater than UT, D and S can be seen as a two-terminal element. This characteristic curve shows their relationship. In this lecture, we are more interested in applying this part of MOSFET. In another word, MOSFET is a resistor on. In lecture 25, we've introduced the inverter constituted by MOSFET, in which the value of RL is much larger than Ron. This is a symbol of the inverter. Sometimes we need the buffer. A buffer is a cascade connection of two inverters. It's their topological. The output of one inverter is connected to the input of another inverter. The whole circuit's input and output forms a buffer. Let's see the input and output voltage form of a buffer. The input is a square wave because the first stage is an inverter. The output of the first stage is an inverted square wave to the input. The output is the input of the second stage, so the second stage inverter's output is inverted to UO1, so UI1 and UO2 have the same phase. And this realizes the function of the buffer. Now we use a simulation to strengthen your impression. Well, this is a simulation of the buffer. Look at the circuit. This is a square wave signal. This is a 2N7000 MOSFET. This is a pull-up resistor with a quite large value. This is a 5 volts DC voltage source. This is the first stage inverter. The second stage inverter's topology and element parameters are the same as the first one. The two inverters form a buffer. This is a 4-channel oscilloscope. The red line represents channel A and is connected to the signal source. The green line represents channel B and is connected to the output of the third stage. The black line represents channel C and is connected to the input of the second output. The signal frequency is 100 Hz. Let's see. In order to have a clear observation, we move down the position of channel B and move up the position of channel C. You can see that the red line represents the input, the green line represents the first output, and the white line represents the second output. That means the input-output signal have the same phase, which realizes the function of the buffer. What will happen if the input signal's frequency is 100,000 Hz? Let's run the simulation. Adjust the time base smaller than before. You can see that the red line represents the input, the green line represents the first stage output, and the white line represents the second stage output. You can see that when the input changes from low level to high level, the first stage output changes from the high level to low level fast. But when the input changes from the high level to low level, the first stage output changes to high level slowly after a period of time, which makes a transfer delay between the input and output of the buffer. You can see the difference between the two times is the transfer delay. In the previous simulation, we found that the buffer becomes no ideal with the increase of the signal's frequency. That is, the output cannot follow the input immediately. Why? We will focus on the structure of MOSFET. Let's review this figure, which is discussed in 24 about the basic principle of MOSFET. When there is a positive voltage between G and S, positive and negative charges will be accumulated on the upper and lower sides of the gate oxide. The value of the voltage determines the thickness of the negative charges below. If there is another positive value between D and S in this condition, the negative charges of D and S can flow through the channel to form the current. Because of the insulation of the gate oxide, the positive and negative charges form an electric field, which makes a voltage difference between the gate oxide. This satisfies the definition that is C equals Q over U. So there are two capacitors between G and S and G and D respectively. As we point out in lecture 46, capacitors can be made artificially with specific value and may also be realized without particular design, but with parasitic parameters. We also need to point out that there's also a capacitor between S and D. So the whole MOSFET contains several parasitic capacitors in which CGS has the greatest impact. Our following discussion should consider the impact of CGS.